Welcome to our webinar on exploring predictive healthcare applications for Diver Platform. My name is Tim Lindeman, Vice President of Business Innovation at Dimensional Insight. I have been leading efforts at Dimensional Insight to explore the possibility of developing predictive applications for our Diver Platform customers. I have the honor to be joined by Dr. David Peterson, Chairman and Director of Technology at Ventana Systems, who will speak later in the presentation. Thank you very much for joining us on the call today. We welcome you to submit questions at any time into the GoToWebinar question window. We will reserve several minutes at the end of the webinar to answer your questions. I'd like to start off by offering some background on why we think predictive analytics is an important topic. This slide originates from Gartner's Analytics Maturity Model. It shows the spectrum of analytics capabilities, beginning with the ability to understand what happened in the past, why it happened, and then using predictive and prescriptive analytics to provide organizations more and more value. With each progressive stage in the maturity model, the analytics capabilities bring an organization closer to the ultimate goal of making better decisions and acting on those decisions. Up to now, most of Dimensional Insight's customers have been using Diver Platform for descriptive and diagnostic purposes. And as our customers are making great progress in accessing more and more data using our product, some are beginning to look at the next stage, which involves gaining additional insight from the data on our platform by using it for predictive purposes. At the time when Gartner published this diagram, only 11% of organizations across a variety of industries had reached the predictive stage of the analytics maturity model. But this is clearly the direction the industry is going, and I suspect this is the reason why many of you are participating in today's webinar. When we take a look at the demand for predictive analytics in the healthcare market, according to a recent survey, 80% of healthcare system executives believe the future of healthcare could be significantly improved through the use of predictive analytics. And 31% said their organizations had already started to use it in one or more ways. Another 38% indicated that they have plans to adopt predictive analytics within the next 3 years. Although we haven't surveyed our customers on this topic yet, we have been asked by quite a few hospitals whether we provide predictive analytics capabilities within the Diver platform. So we clearly see strong interest in the market. To get a better understanding of the market for predictive analytics in healthcare, our team did a fair bit of exploration from various media sources to find out which hospitals are publicizing their predictive analytics initiatives. There are a surprising number of hospitals that have been written about, and the names on this page are just a small sample of some of the better-known organizations. And here are a few examples of articles we found. Harvard Business Review reports how machine learning is helping to predict heart disease and diabetes. Boston hospitals are using machine learning to manage expensive illnesses. And predictive analytics is helping hospitals manage their nursing forces. There are a great many articles out there, and we are seeing more published on almost a daily basis. Another indication of the healthcare industry's interest in predictive analytics is the number of seminars and events focused on topics like deep learning, machine learning, AI, as well as predictive analytics. I haven't had the opportunity to attend one of these events yet, but I have gone through the agendas, and they are filled with hospitals speaking on a variety of use cases and a bunch of vendors promoting their tools and solutions. In addition to these specialty events, predictive analytics has been an important topic at many of the larger trade shows. So I hope the last couple of slides have left you with an impression of the incredible hype around predictive analytics in the healthcare industry, as well as the larger market in general. Which brings us back to Gartner and their famous hype cycle. Predictive analytics is just one label being used for predictive technologies. In the 2017 hype cycle for data science and machine learning, Each of the technologies in the red boxes have a close relation to predictive analytics. Most of these technologies are very near the peak of inflated expectations, with the exception of simulation, which David is going to talk quite a bit about later in the webinar. So what does this mean? While there is a lot of hype and a huge spectrum of use cases for predictive analytics, we have yet to see a clear standard set of applications emerge with quantifiable and consistent benefits. While there are projects with sizable budgets involving some big-name technology and consulting firms, many of the projects appear to be skunk works, led by individuals who are enthusiastic about data and know a little R or Python. So I would argue that the technology appears to still be in the later stages of early adoption. And if Gartner is right, we will probably have to go through the trough of disillusionment before predictive analytics is ready for prime time. We put caution in big red letters here, and there are a couple more cautionary slides to follow, but we think this is the right time to take a serious look at predictive analytics and to start working with our customers who want to be part of the innovation that is going to have a huge impact on the future of healthcare. This slide shows another reason we should be cautious. While most of the stories we read about predictive analytics talk about the successes, there are also a great number of unpublished stories of failure, with one big story making the news last year. Here is one last cautionary slide. With predictive analytics, expertise is required, and we do not say this lightly, because expertise is also required for descriptive and diagnostic analytics. But the expertise required for predictive analytics is a big step beyond. One reason for this is there is a risk of predicting or prescribing the wrong course of action using a black box algorithm that few people can understand. Another reason is that there are many different approaches to predictive analytics, including machine learning, regression, and other methods of pattern recognition, as well as simulation, which is a completely different approach that David will explain shortly. Taking into account all of the hype and the opportunity to innovate in a technology that could be revolutionary for the healthcare industry, we decided to reach out to Ventana Systems, another company in the MIT ecosystem that has incredible experience in predictive analytics. Our plan is to partner with a handful of Diver Platform customers to jointly develop a set of standard predictive applications with measurable benefits that we can offer to the larger healthcare market. So, with that lengthy introduction, I would now like to introduce Dr. David Peterson of Ventana Systems to explain how we plan to develop our predictive applications.
Ventana is a team of a couple dozen applied mathematicians located across the U.S. with operations also in the U.K. and Europe. Most of our people have advanced degrees from MIT. We are world-class at helping our clients make realistic simulation models, typically involving human factors as well as physical, organizational, and finances. We provide the standard simulation and analysis software for our field with over 1 million users worldwide. Ventana's predictive technology may be understood as an alternative to traditional big data pattern recognition. Instead of looking for recurring patterns and hoping they will repeat, we help our clients make predictive simulation models to understand the causes of observed trends. Each model takes advantage not only of data, but also of the knowledge and expertise of experienced people. Pattern recognition is ideal for complex but repetitive situations such as face recognition, voice recognition, chess, and quiz shows. A pattern recognition system can be trained automatically, digesting large databases. But they don't help much in situations where the goal is to improve the performance of a company or hospital, where improvement comes not from repeating what was done before, but from finding improved new approaches. Simulation models can identify opportunities that aren't directly seen in the historical data so they can support improvement and innovation. But a good simulation model can't be generated by data and algorithms alone. Human knowledge, experience, and credibility tests are important in developing good predictive models. Realistic simulation models have their roots in physics, engineering, and psychology. As early as the 1960s, models were developed that combine physical, financial, and human factors. In the 1970s, compute-intensive algorithms from code breaking and control theory were adapted to use data to calibrate and test such models such that they became useful predictive tools for improving the performance of business and healthcare systems. These applications have continued to evolve and improve ever since. How do good predictive simulation models get built, and what makes the difference between a good model and a bad one? Constructing an accurate predictive model starts with defining how the desired outcome could be measured and brainstorming a range of actions that might be taken to achieve the desired outcome. Cause and effect structures are then built using expert knowledge. The same experts then test the model over a wide range to be sure it is realistic and robust. Algorithms are then used to fine-tune the simulator to match history, and then it can be used to find the best path forward. Predictive technology is often used to solve problems, whether it be making operations more efficient, reducing length of stay, or a variety of other issues. The best approach is to start by clearly defining the problem. For example, we start by meeting with your hospital's experienced people as a team to define the problem or possible problems. The combination of the team and the technology enables the problem to be defined crisply in specific terms of desired results, hazards to be avoided, and possible actions that might be taken to achieve the aims. In our experience, this precise defining of the problem and its possible solutions is itself helpful because it often clarifies and expands the team's vision of possible futures and options. The problem is well defined when the goals are clearly defined and there is a list of possible policies that might achieve the goals. A predictive model works by predicting how close each policy comes to meeting the goals. So once the problem is defined in terms of policies and goals, the next step is to connect the policies to the goals with chains of cause and effect links. We work with your team to create these structures in the model. One of our skills as modelers is to be able to take an amorphous word salad and from it construct quantitative cause and effect models. The modeling techniques allow anything important that can be described to be included in the model, even if it has not been traditionally quantified. For example, time pressure, fatigue, and morale are commonly show up in our models. The team participates in making sure that the model components are realistic and consistent with the kind of expertise that comes only from deep experience, from people who've lived with the system being modeled. Once the team has defined the model, we put it into our software to allow the model to be quickly simulated. With the model running, your team simulates a range of possible scenarios to test the realism of the model. Your team judges whether the responses of the model are consistent with their knowledge and intuitions. These credibility tests cover the widest possible range. For example, a model of hospital operations is a model not only of how the current operations go, but with changed parameters can be a model of what your operations could become under all possible policies. Once the model has been determined to be robust and realistic, able to credibly deal with any situation, it's time to tune the model to match your specific situation. We use calibration algorithms to adjust the parameters of the model so that the model matches the data. Specifically, we pretend that the model is being used some number of months or years ago and ask it to predict what would happen. When this retro prediction matches what actually happened, the model has been calibrated, or as we say, tuned. In this tuning process, data meshes with the expert knowledge of the team to make the predictions of the model as accurate and reliable as possible. What the model predicts depends on facts such as the laws of physics. But the future is also determined by what you do, your policies. Therefore, every prediction made by the model is a contingent prediction. The prediction is contingent on what policy you follow. Therefore, you can use the model to find out which policies lead to the best outcomes and why. You use the model to make predictions for each of many policy options and see which predicted outcomes are the best. This contingent prediction capability allows you to use the model for decision support. Where appropriate, predictive models are even now being used to automate decisions. Using contingent predictions, you can explore a wide range of policy options and magnitudes to find the very best path forward to maximize performance and minimize risk. The fancy name for this is decision optimization. Now that I've walked you through our process, I'd like to share with you a couple of actual applications in healthcare. First, Ventana served as part of a large study in South Florida to improve mental health care. Our customer was proposing to commit to a pay-for-performance contract. They would commit to make big investments, but they would be compensated only if the result was cost savings to the community and improvements in mental health outcomes. We worked with them to make a predictive model taking into account the interaction of doctors, hospitals, patients, communities, pharmaceuticals, and criminal justice. The model was used to explore which investments or policies would reduce the costs of the overall system and improve the health outcomes at the same time. The client's use of the model enabled them to discover risks that no one had noticed before and to incorporate these in the pay-for-performance contract. There were other benefits from the model too. By linking expert knowledge and big data in one consistent framework, the model revealed that some of the data were flawed. For example, before the model was applied, no one had noticed that the data recorded twice as many people flowing into the jail each year as were being released. This same flawed data was to be used in the system, so its correction was important. An association of the towns and cities of Massachusetts has also used Ventana technology to devise new strategies to use timely investments and interventions to anticipate and prevent expensive medical events. For example, expensive meds might be justified if they prevent even much more expensive hospitalizations. The Massachusetts group used the model to rank the relative importance and payoffs of a wide variety of policies, including well-being programs, preventative treatment, and compliance follow-up. The results enabled improved policy optimization. In addition to these direct cost and health benefits, the model uncovered an unexpected side effect. The model showed that the indirect benefits of improved employee morale would be even bigger than the immediate benefits and cost savings. The South Florida and Massachusetts examples are only two of many applications of our technology and tools to improving healthcare. So that concludes my summary of Ventana technology and how it can add predictive capabilities to the Diver platform. I appreciate your attention and the opportunity to present it to each of you. Tim, thank you. Back to you.
Thank you very much, David, for being part of our webinar today. We are very excited to work with you and Ventana Systems and can't wait to begin working on our first application. I would like to finish off the presentation portion of the webinar today with a few takeaways. We believe there are many potential benefits of predictive analytics in healthcare, ranging from reducing cost, improving productivity, improving quality of care, and improving the overall population health. The market interest in predictive analytics in healthcare is huge, but there are quite a few reasons to be cautious. Dimensional Insight customers have a fantastic platform on which to build predictive analytics applications. Diver Platform has comprehensive data management capabilities with automated business rules and collaborative data governance. We can integrate with Ventana Systems simulation technologies as well as R for pattern recognition capabilities, opening up a vast palette of data science tools. Diver platform also includes business intelligence for reporting and analytics, and we plan to integrate predictive analytics within our analytic dashboards and ad hoc analysis tools. Finally, Ventana Systems brings over 30 years of predictive analytics experience and powerful simulation capabilities to our team. So, how can you participate? We are looking to assemble a small group of diver hospital customers who are interested in being innovators in predictive analytics. We plan to work with the group to identify common use cases and a standard set of requirements. We will then develop the predictive applications with Ventana Systems, deploy them at each of our partner hospitals, and refine the applications as the hospitals use the product and provide us feedback. We hope some of you on the call today will be part of this partnership. If you are interested in learning more about our partnership opportunity, or if you're interested in following news of our developments, please let us know in the survey we will be sending out after the webinar. You can also reach me by email, and I would love to connect with you on LinkedIn, where I will be sharing updates from time to time. At this time, David and I will spend a few minutes answering some of the questions we received. All right, so I'm going to start with one of the questions from the audience. I also have a few questions that I prepared as well, but I think this would be a good question for you, David. Pharma is a huge component of healthcare costs. Most predictive companies have a very difficult time providing predictive information on this. How is DI different, or how would DI and Ventana working together be different with this?
Well, this is David. We've had a lot of experience with pharmaceuticals going way back, so I can empathize with the observation that pharma is not easy, but pharmaceuticals are such a big fraction of some medical costs that it's important to deal with. So our experience is that pharmaceuticals can be understood and can be made predictive. And this ranges all the way from usages in places like the Massachusetts consortium that we described in the beginning of the talk. And also we've done work directly for pharmaceutical companies, finding out to what degree medications are effective, and even under what conditions they can gain market share in competing with other medications. So we see pharmaceuticals as an area where we have a proven record in being able to apply predictive techniques. I hope that answers the question.
And we can add more nuance to that as well if you want to follow up with any follow-up questions. I have another question for you, David. And can you tell us a little bit more about how a simulation model works with our existing data at a hospital or the data that we have in the Diver platform?
Yes. The main use of existing data is to test the model and to calibrate it. So we like a lot of data, especially if it covers a long time span, in order to identify patterns and to test whether the model is doing a good job. So as mentioned before, the model always thinks it's predicting. And so if you initialize the model with data from months or even years ago or even decades ago and say, okay, model, if you're so smart, predict what's going to happen, and see if it correctly predicted the past data you've got. And almost always a model will fail that test, and sometimes you can make it an accurate predictor over the historical period simply by adjusting a few parameters. The fancy name for that is parameter estimation or calibration. Sometimes the discrepancy between what the team thought were the causes of things and what the data shows reveals that there's a missing link, that there's something not in the model that needs to be there. This has happened not only with organizations like hospitals, but even in physiological models we've made of things like the way the pancreas regulates glucose in the bloodstream. There was a case in which the preeminent doctors in the field of diabetes had described all of their knowledge about how the beta cells in the pancreas detect blood sugar and react to it by emitting insulin. And a model of all of those factors, when given a glucose tolerance test, gave results which no human patient had ever exhibited. And it revealed that, this was some time ago, it revealed that, unknown to medical science at that point, the model proved that there had to be something in the pancreas that detects not just the level of blood sugar, but also the rate at which the sugar is changing. And when we added that component to the model on a speculative basis, we discovered we could get predictions that mapped out what you actually see in human glucose tolerance curves. So the data, historical data, is a potential gold mine for getting to the truth of what it would take to improve outcomes for patients or efficiency of operations.
All right, so let me change the topic slightly here. You mentioned some use cases in which simulation is a good approach in healthcare. Are there some use cases where pattern recognition would be the preferred approach?
Yes, there are any case where you have a highly repetitive situation and you're not attempting to change it so much as just understand it and anticipate things and recognize the pattern earlier and take some sort of action to be more efficient. Pattern recognition can be very effective. So this has a long tradition in medicine, all the way back to before it had the name big data or pattern recognition. It was called risk factors. So people would look for correlations between various things and disease states. So smoking became a widely recognized risk factor, even when it was controversial as to whether the case had been proven or not, the connection between smoking and various diseases. And this tradition of looking in the data for patterns that seem to be recurring and trying to take advantage of those patterns is a long and honorable tradition. So our approach of making cause and effect models is sometimes stimulated by pattern recognition and sometimes is synergistic with it, and other times pattern recognition is itself the preferred approach, and in other situations you can only get where you want if you understand the cause and effect behind it.
Okay, one follow-up question on that. Is it possible to use both simulation and pattern recognition together in your approach?
Yes, in two ways. First of all, the process of exploring the data to brainstorm what the cause and effect might be is a form of pattern recognition in a way, getting to know the data in ways that weren't obvious before. And we sometimes use statistical tools just to look at and understand the data before making the cause and effect model. In some cases, we've actually simultaneously used two different approaches to solve the same problem. So in one case, we had a cause and effect model, and in parallel with that, we used a neural network to see if it could solve the same problem. This had to do with predicting expensive test outcomes. And in the particular case I'm thinking of, one was a winner and one was a loser, but that's not always the case. In that case, the neural network scored a perfect score on the training set, but was absolutely useless outside that. And it turned out that it was simply relying on false correlations and coincidences to perform well on the training set. And the causal model provided a big breakthrough. But in other cases, neural networks and pattern recognition can solve the problem using only that approach and serve very well. So it all depends on the nature of the problem.
Okay. We have another question from the audience, and I think this is a very good one. Even large insurers have found they don't have large enough data sets to build comparison models. How will you build a large enough data set for viable comparisons with the relative limited data available from most hospitals, or even large health systems for that matter?
This is a great question. And it has one of the hidden strengths of simulation models is if you have limited data and you're trying to extract maximum possible use from what you've got, you need a model. In the old days, statistical textbooks talked about sample size, and if you didn't have enough precision or enough confidence or low enough risk, then you needed a bigger data set. Modern textbooks in statistics, which emerged from what was once secret during World War II, having to do with code breaking and radar technology. Modern books on statistics start out with phrases like, given a dynamic model of the system you are measuring, how do you best use the measurements? And the modern techniques are computer intensive, and they're not typically taught in Stat 101 in college. But they are used to basically decode where you have typically limited data or data that's corrupted in some way, a lot of exceptions in the data or noise or changes in measurement techniques. And so things like correlation simply don't work. But if you use that data and process it using simulation models, you may be able to learn a lot from it. So predictive simulation models can be seen as well, from a theoretical basis, they are the best way to maximize what you can learn from the data. So the only question is, if you have the luxury of a lot of data and if the patterns in the data are highly repeatable, then you can avoid the expense of understanding cause and effect sometimes and get some good payoffs from just using brute force pattern recognition techniques. But if you're in a situation where the data is scarce, then you definitely want a model to help you with what you've got.
All right. So how much time does it usually take to carry out a predictive project from defining the problem to deploying the solution?
It would be wonderful if I could say one specific number, but experience has shown that for typical hospital magnitude problems, it takes anywhere from 2 weeks to 6 months or more, and it's not very predictable. The idea of getting down to cause and effect, if you think about it, is a little bit like the whole process of science. So you can't really predict whether the thing you're studying is going to have a quick payoff or not. But we have, at the optimistic end of the spectrum, sometimes simply getting the group together and going through the cause and effect structure of the problem will cause everyone to say, oh, aha, now we know exactly what to do, even before we go anywhere near the data, because just qualitative numbers make it obvious what you have to do. And in other cases, there are ambiguities and subtleties, and it has to be resolved quantitatively, and then that requires more work. Usually, most of the work involves the data, not the model itself. So we can construct models quickly and efficiently. The hard part is making sure that the data is understood and using the model to extract as much wisdom as can possibly be found in the data. And that's a combined human technology process, and sometimes it happens very quickly and sometimes it takes a while.
Well, that leads me to my last question. And this is where our customers and their data come in, and they're all using Diver platform. So there's some commonality there. Do you think it will be possible for us to work with a handful of hospitals, come up with common use cases, and then to develop a model and an application that would be applicable for all of them, and potentially we would be able to reuse that application in the larger market.
Yes, with a qualification which comes with mixed news. We're living in a case like that right now, where we were hired by one location and did a study for them that completely turned around their operation, and they were very happy. Global headquarters sent a dozen people to go and look at that, what had been done with the predictive model, and immediately said they wanted about 100 of them to cover all their locations worldwide. And we're now on location number 4, and we've discovered that that the other locations are not mere repetitions of the first one. They share the common model, the common structure, but the parameters are very different, and what's important in one place may be unimportant in another place. So we've learned a lot from that, and so it's a good news, bad news situation. The bad news is, just as patients can be very different one from another, hospitals could also be very different one from another. The good news is that we've discovered in situations like that there's a lot to be learned from the other hospitals. So applying the same predictive product across multiple hospitals becomes a synergistic opportunity for all of the users to benefit and learn not just from their own data, but from each other. So that's been very exciting for us.
All right. Well, thank you very much, David, and thank you to everybody who joined us today. We'll be sending out a survey shortly after the call, and we hope that each of you can take a minute or two and give us some feedback. And we'll also be posting a recording of the webinar for you to watch again and to share with others. So I hope you have a great day, and thank you for joining us.